All right, so this is where we left off. We were talking about comb filtering, and just to refresh your memory, we learned about the different kinds of things that can happen when two identical sounds run into each other slightly out of phase. So cancellation can occur, reinforcement can occur, and other things can occur too. But those specific examples are for sine waves, single frequencies. But real sound is more complicated than that. Real sound has lots of frequencies all at the same time. And so usually a phase offset is the result of a time offset, usually. So you have a copy of the sound that is offset in time somehow. Like you have two microphones picking up the same sound, but those two microphones are two different distances away from that sound. Or the sound reflects off of a wall and gets back to the ears, and it took longer to bounce off the wall than it did to come straight to your ears in the first place. Now you got two copies of the sound hitting you at a different time. So those are just two examples. There's more of how you can end up with two copies of the exact same thing, but at different times. So when you have that difference in time, which is, let me quit this actually, which is what this is representing. So there's a difference in time, and if that time represents the period, meaning the amount of time it takes for that frequency to complete one cycle, then that sound gets reinforced. Those two copies reinforce each other perfectly, and you get a boost. But that same exact period of time could represent for another frequency a 180 degree phase difference, which that frequency would cancel out based on that specific time offset. And this happens in octave multiples or harmonic multiples. So you end up with a whole bunch of frequencies that cancel out, right? And a whole bunch of different frequencies that reinforce. Yeah? And then, of course, everything that's in between. We know that there are some phase offsets that result in no change in amplitude. And we know there are some phase offsets that result in a small change of amplitude, but not a full reinforcement. And so that's where you get this continuous pattern. Now, this is an actual comb filter that I recorded. I believe I just played the same sound out of two speakers and put one speaker 1 millisecond farther away from the microphone and recorded the result, and this is what I got. And we call it comb filtering because when you graph it like this on a frequency response graph, it looks kind of like a hair comb. Okay? Yeah? So we remember this from last time, yeah? And we heard it last time. I played the sound, you could hear what it sounds like. Now, let's try to see if we can do some math to demonstrate our understanding or lack thereof of this principle. So here's just rough calculation in your head. See if we can start visualizing what these time offsets do. So imagine a 250 hertz sine wave. And now imagine that you have two of them. But the second one is 90 degrees out of phase with the other one. What difference in time would that be? Like, what amount of delay would have to be applied to that second sound? Well, let's try to visualize this a little bit. If I kind of graph that wave, okay, and I say that this is the 250 hertz, then what would be the wavelength of this of 250 hertz? Well, that would be 1,000 divided by 250. What's that? 4. 1,000 divided by 250 is 4. Okay? So that's the wavelength. And we know that so it's 4-foot wavelength. And we know that sound travels about 1 foot per millisecond when we're kind of guessing in our head. So between here and here, that is 4 feet, yeah, or 4 milliseconds, right? So this would be 0 milliseconds of delay. This would be the 4 milliseconds of delay, which means 2 milliseconds would be here, 1 millisecond would be here, and 3 milliseconds would be there. Everybody with me so far? Okay, so, well, what are the phase relationships? Well, this one is 0 degrees, this one is 360 degrees, this is 180, and this would be 90, and this would be 270. So, what delay applied to one of two 250 hertz sine waves would make it 90 degrees out of phase with the other? 1 millisecond. Yeah. Make sense? Did I lose anybody there? Okay. Same scenario. What delay applied to that 250 hertz sine wave would make it 270 degrees out of phase with the other? Yeah, 3 milliseconds. Using the same process. Okay? All right, so we understand the basic idea of how a time offset can result in a phase difference between two sounds at the same frequency, yeah? Now let's take that idea and kind of scale it up now to being able to predict all of the frequencies. That would be a 180 degree phase difference, and they would cancel out. And all the frequencies that would be a 360 degree or 0 degree phase relationship, and they would reinforce. We just want to know, what are the cancellations, what are the reinforcements? Well, it's not really that hard of math. This is how you could figure that out. So we are using a variable I here, and I is an integer value greater than or equal to 0. All integer values greater than or equal to 0. So you start at 0 and you keep going forever. Okay? And then t, in this case, represents the time offset. So t equals time. However, this is in seconds. Okay? Not milliseconds. And so if you wanted to figure out which frequencies would be canceled, and you just kind of go through those I values. So this Fi, F stands for frequency. So frequency 0 that gets canceled out would be 2 times 0 plus 1 divided by 2 times the amount of delay in seconds. And you would get the cancellation. Then you go to 1 for I. And you do 2 times 1 plus 1 divided by 2 times the delay time, and you get the second cancellation, so on and so forth. If you're looking for reinforcements, it's a very similar equation. You're just not multiplying the values by 2 anymore. So you're just doing, for the first reinforcement, it'd be 0 plus 1 divided by the time. And then for the next reinforcement, it'd be 1 plus 1 divided by time. And you just keep going forever and ever and ever, and you'll get them all. So let's try it. Everybody ready to try it? I'm getting some no's.
Sorry, I just need to take notes.
Okay. So here are those two equations. I've left them on the slide here. So if I have two equal signals that arrive at a listener 1.5 milliseconds apart, they will comb filter, right? If they are equal signals arriving at your ears 1.5 milliseconds apart from each other, they will comb filter. The question is, what frequencies get canceled out and what frequencies get reinforced? And just so that we're not here for the rest of our lives, because you could keep doing this math forever and never run out of answers. I just want to know the first 3 cancellations and reinforcements. So the first thing is I want to figure out what is T. Okay, so T is going to equal the time in seconds. So what is 1.5 milliseconds in seconds?
1,000 divided by 1.5.
No. Close, though. Okay, so what is, well, let's say, what is 1 millisecond expressed in seconds? So 1 millisecond equals 0.001 seconds. Because the milliseconds means it's 1,000 milliseconds per second. Okay? So you're really close. You're actually going to divide by 1,000, right? And then you get it. So it's going to be, T is going to be equal to 0.0015. Yeah? Okay, so now that we know that, we can do this. So I'm just going to start making a list here. Let's do the cancellations first. And we start at 0. So I'm going to say 0C equals, and then I'll do 1C equals and 2C equals. Those are the 3 I'm going to do. And those are my I values, 0, 1, 2. So now I'm going to do 2 times 0 plus 1 divided by 2 times 0.0015. All right, how does that work out? Well, here's how I would run that in pCalc. So I'll start doing the bottom part first. So 0.0015 times 2, I get 0.003. I'm going to just put that into the calculator's memory. So remember that number, I'm going to need that. And then I'm going to do 2 times 0 plus 1. Well, 2 times 0 is 0, right? So it's just going to be 1 divided by 0.003, and I get 33 hertz. That's the first frequency that gets canceled out. Yeah? Okay, so next one, I'm going to run out of space here, so that's okay. So we'll say this will be 2 times 1 plus 1 divided by 2 divided by 0.0015. Okay, so this is going to be, well, I'll move it over here so you can see. So the bottom part is the same, right? So I don't have to do that again. That's why I'll put it in the memory so I can just use this number over and over again. So now we're going to do, it's 2 times 1 plus 1. So 2 times 1 is 2, plus 1 is 3. So 3 divided by that number, and I get 1,000 hertz. You could also call that 1 kilohertz. Yeah? Okay, so now let's do the third one. So this is going to be 2 times 2 plus 1 divided by 2 times 0.0015. So that's going to be 5. 2 times 2 plus 1. So 5 divided by 0.003. And I get 1,666.67 hertz. 1.67 kilohertz, if you wanted to do it that way. Yeah? Everybody with me so far? Okay, well, let's do the reinforcements now. Reinforcements, using the same 0, 1, 2, 3, would be, let me just give myself a line there so I don't forget where I am. So this will be the first one, 0c is going to equal 0 plus 1 divided by 0.0015. So that will be 0 plus 1 is 1 divided by that, and I get 666.67 hertz. Hopefully you're starting to see the pattern here, right? I mean, the answers here are in multiples because that's how sound works. That's how frequencies work. Okay. 1c is going to be 1 plus 1 divided by 0.0015. That would be 2 divided by that number, and I get 1,333.33 hertz. And then we do the next one, and that's 2 plus 1 divided by 0.0015. And that's going to be 3 divided by, and I get 2,000 hertz. Yeah? Makes sense? There you go. You can keep going on this forever and graphing this. And you would, if you graphed it plus all the things in between, which I'm not really teaching you how to do all the things in between, you would get a graph that looks like this. Like just plotting the numbers we could do, you would end up with all the red dots, basically. Yeah?
Can we go back
To which one?
to that? To, yes.
What does the C stand for in this equation?
Oh, I should have done R's here.
Okay.
I'm just cancellation versus reinforcement, just so I remember what equation to do.
Oh, okay, gotcha.
Yeah, sorry, my mistake. Yes, Sam.
So I doesn't represent a frequency. It represents like
An integer.
lowest number of,
Yeah.
Okay.
Yeah.
So
I mean, yes, it represents ultimately a frequency,
okay.
but to find it, we're just using that So what we're really looking for is first cancellation.
Right. So 1 is the first, or 0 is the
Yeah,
first.
it's the zero base.
Okay. So it's the lowest frequency that is going to be canceled or reinforced.
Exactly.
Okay.
That's the idea. All right, I got more of these. You want to do another one?
Sure.
Why not? Okay, here's another one. So you got two loudspeakers. One is 3 feet upstage of the other. In other words, 3 feet farther away from the audience. They will comb filter with what first 4 cancellations? So what would be the first 4 frequencies canceled out in that scenario if you just play the same sound out of 2 speakers and they arrive at the ears 3 feet apart from each other? Okay. So before we can figure this out, we got to turn that 3 feet into time. And sound, what is the speed of sound? 1,130 feet per second when we're doing it with calculator, right? And how many feet per millisecond is that?
Not 1.
Yeah, but specifically, what is it?
Is it the 1.13?
There you go. 1.13 feet per millisecond. Okay? You just memorize that. 1.13 feet per millisecond. Okay? Because you're gonna use that over and over again. Okay, so 1.13 feet per millisecond. That and we've got 3 feet. So here's just a little shortcut. That 1.13 is a magic number, and you can use that to convert either direction. So if the distance value is always going to be larger than the time value, okay? Just because of how this works, right? Because it's 1.13 feet per 1 millisecond. So if you're going from feet to milliseconds, you're going to get a smaller number if you do it right. And if you're going from time to distance, you're usually going to end up with a bigger number. So that's just a way to check your work. Remember that. Going from distance to time should result in a smaller number, and going from time to distance should result in a larger number. So if you do the math and you get the opposite of that, you know you've done the math backwards. Okay? So if we want a smaller number, the only question is, do we multiply or divide that 3 feet by 1.13 milliseconds? Yeah, we want to divide because we want a smaller number, right? So I'm going to say 3 feet divided by 1.13. What is that? 3 divided by 1.13. 2.654867.257. Yeah? Now that's milliseconds. So
2.7
I would do 6.5. 2.65 milliseconds. Okay, now I need that in seconds, right? So if I divide that by 1,000, I will get it. So now t equals, for purposes of this equation, 0.0027.
Jason, would you do, instead of dividing it by, dividing by 1,000, would you divide by the 1,130? Is that right?
No, because it's 1,000 milliseconds in a second.
Oh.
Right? Yep. Yeah, good catch. Okay, so let's try this, shall we? So I'm going to do cancellations. So my first cancellation I'm going to call 0 for C, cancellation. And this is my time value. So I'm going to first do the times it by 2 part. Right? So I'll say take that number times 2, and I get 0.00530973.5. And I'm going to put that in my memory so I don't forget it. And now I'm going to do, this will be 2 times 0 plus 1 divided by 2t. And t is, remember, up there. So this will be 1 divided by this number I've remembered. Yeah? So 1 divided by that number I remembered. I get 188.33 hertz. Did anyone else get that? Sam got that. Charlie got that? Okay, we must be right. Okay. Next one would be cancellation 1, and that's going to be 2 times 1 plus 1 divided by 2t. So this will be 2 times 1 plus 1 is 3. So 3 divided by that number I remembered. I get 565 hertz. Anybody else get that? Ben got that? Now, depending on how you rounded that t value, your frequency might be not exactly 565. And this goes into that category of could I hear the difference, right? So if you're, depending on how you end up rounding that t value, when you answer it like on the Canvas quiz, you might be off from mine, but I do build a little bit of a tolerance in there for that rounding. And even if it still grades you wrong, I still will look at it myself and just do a quick judgment call of like, could I hear that difference? And if I couldn't hear the difference, then I'll give it to you, okay? So close counts for most of this math we're going to do. All right, I need to do 4 of these, so let's do the next one. So this will be 2 times 2 plus 1 divided by 2t. So this will be 2 times 2 is 4 plus 1 is 5. So 0.5 divided by 2 times t, and I get 941.67 hertz. Anybody else get that one? Ben got that one.
Can you go a little bit slower? So you're,
Yeah.
you do 2 times that 005309 number? Or,
Well, no, the 0053 has already been multiplied, but that's already multiplied by 2.
oh.
Right?
so
'Cause
then-
t is
you're
point
dividing
zero-
it by 5.
T is 0.0027, right?
Yes.
That's what t is, but the equation is 2 times t, right? So I've multiplied it by 2, and I just put that in the memory of the calculator, so I don't have to do that over and over again.
I see.
Yeah?
And then so then once you find the top of the equation, you're just dividing it by 2.
You're just dividing it by, yeah,
Or
the
by
2
that
2
one.
times t.
Yeah. Yeah.
So this number that I've remembered is 2 times t.
Okay.
You with me?
Yes.
Okay. Other questions? We got one more cancellation to find here. We'll call that 3c. And that should be 2 times 3 plus 1
7.
divided by 2t. So 2 times 3 plus 1 is 7, right? So we're going to do 7 divided by 2 times t, which is 0.0053. And I got 1,318.33 hertz. Yeah? Brooke got that. Anybody else get that?
Yeah, close enough. I'm not getting the 3 repeating, but
What did you get?
I got 1,318.333212.
Yeah, that's just because of you rounded t a little bit differently than I did.
Okay.
That's all.
I also got 1,320 point.
Yeah, so you
I feel
probably
like that's rounded.
you probably rounded t all the way back. You've probably been using literally 0.0027 times 2,
Yeah.
as opposed to where we started with, which was this 0.002654867. Like I never rounded it in the calculator. I just kept it going. But either is right. I mean, all of those answers are right.
Or
Okay. Right-ish. You know.
Close enough.
Yeah. Okay. There you go. So there's the answer. Those are the 4 frequencies. That will get canceled out in that scenario. Other questions? Ready for the next one? Okay. If a comb filter has its first reinforcement at 1.5 kilohertz, what would the first cancellation be? All right. So, yes, exactly. So I'm giving you a different part of the equation here. We have this observable reinforcement at 1.5 kilohertz, and we want to find out, well, what would be the cancellation that would be occurring right next to that? Well, to figure this out, we would first have to take this reinforcement equation and solve it for t, because we got to find out what is the time value that resulted in that 1.5 kilohertz reinforcement. Now, I'm not super great at algebra, but I have friends who are, and they tell me that solving this equation for t, it looks like this. T equals I plus 1 divided by fi.
Yeah, because it's just multiplying and dividing
Yeah.
both sides by f on t.
Yeah, I guess. So, so that's the first thing we got to do is we got to find t, right? So we find t using this equation. So I plus 1 divided by frequency I. So if it's first reinforcement, what's the value for I? 0, right? So t equals 0 plus 1 divided by
The 1.5 kilohertz.
Yeah.
times
So it would be 1500 hertz.
Oh, okay, got it. Okay.
Yeah. So let's try it. So 0 plus 1 is 1, divided by 1500, and I get 0.000666667. Yeah. I didn't know how many 6-7 jokes I'd be feeding to Brooke today in this comb filtering. So
I'm being really well behaved though.
I can't wait to see the comments on YouTube. It's
Yeah.
so great. Someone's gonna go through and get a timestamp of every single one.
okay, so that's t. 0.00067. Yeah.
Every time he says it, he looks at me. And he's so close.
Because I know you're so obsessed with this joke.
I am. I can't help it.
Keep waiting for you to do something.
Hey, Jason,
Yes.
on mine it says 6.7
Yeah, I got the
minus,
same.
or radical minus 4.
I got the same thing.
Yeah. That's
That's
just
a way to
that's just your
describe
dopey calculator.
it. This is PCalc. This is your calculator, Jason.
Well, you got to put it in the smaller mode so it doesn't do that.
Okay.
How
How do I do that?
that just means it's just shifting the decimal 4 places.
Okay.
That's all that means.
Okay, understood.
That minus 4 just means we've moved the decimal 4 places, just so you can actually see what's going on.
Gotcha.
Okay, yeah, I see.
Understood.
All right. Okay, so that's t. We got it. And I want to find out what the first cancellation would be in that scenario. So now I'm going to switch over to this equation. So now I need to know 2 times t. Yeah? So I've got t already loaded in my calculator, so I'm just going to multiply it by 2 while I've got it here and plug that into my memory. Okay, and so now I'm going to do 2 times I, and what would I be in this scenario? 0. 0 plus 1 divided by that number, which is 2t 0.0013333. Okay, so 2 times 0 is 0, so this is 1 divided by that number, and I got 750 hertz. Charlie, you look confused. Did I lose you? Did I do it wrong?
So it's it's 3 divided by that number?
No. 2 times 0 is 0, so 1 divided by.
Oh, you're right, sorry. My bad.
I
Yeah.
got 751.
Yeah.
But I think it's because I didn't have as many threes as you.
Yep. You could not hear the difference between 750 and 751 hertz. If I played them separately. You want to prove it?
No, I was just saying because.
No, like I'll prove it.
Okay. I don't doubt you. I 100% believe that.
This is
I
not a
would
doubting
be able to
thing
hear
anymore.
it.
Jason just wants to prove himself.
Yeah, it's
Jason
just
wants
my
an
number is
excuse to-
750.
I just wanna make my point.
87. And so then it'd be 752.
I'm right there.
Jason just yearns for a sine wave, that's all.
Let's do it, why not?
Actually, it's
Normal when
probably
Jason
already in
says
here.
We shouldn't ask any more questions, but does this instead.
Sam, do you like the PCalc app?
It's good.
Okay.
Okay.
It doesn't do
Um,
all of the fancy stuff that my actual calculator does, but
I think I might have left mine in India.
it's good to have just in your pocket.
Okay. So let me turn this off.
How did you go to India?
So here's 750. Yeah?
Mm-hmm.
751.
I hear it.
You know, Jason, I.
750.
Yeah, it's just
Yeah,
work.
it sounds different, Jason.
Right, barely.
Now, but watch what happens when I put it together. So if I take 750 and combine it with 751, they interact. So you can hear it when they interact. But hearing them just separately, it's really, really hard to tell the difference.
That's what it sounds like when I stand up too fast.
You should probably get that checked.
Yeah.
It's anemia, I know what it is.
Okay. There you go.
That was awesome. I think those was for like visuals.
Okay.
Okay.
Glad I could please. Ready for the next one? Okay. How far would one of two loudspeakers need to be offset to make a comb filter with the first cancellation at 640 hertz? So ultimately, I'm looking for a distance here.
Oh, so you
Right.
define and then turn it into
Yeah. So ultimately, I need to get t, and then I'll convert time to distance. Okay. So so I'm going to need to use the solve for t version of the cancellation equation, which I have included for your convenience here.
Will they be included in the canvas?
No. I mean, the
Are you
slides
not
are on
voting?
Canvas,
I was
but
gonna say,
No,
but
I
this is
meant,
on the
like-
slide.
Like, on the quiz?
no.
Open no question.
Open no question mark.
I mean, you're doing it at home, so I mean,
Word.
get the answer by any means necessary, as far as I'm concerned.
By any means necessary, you say.
Okay.
You watching the lecture will take you
Yeah, right.
All right. So solve for t. 2 times I plus 1 divided by 2 times the frequency. Okay. So 2 times, what is I in this scenario? 0. Plus 1 divided by 2 times, what's the frequency?
600. Oh.
Yeah? That's the equation. Okay. So 640 times 2. I just like to do the bottom first usually, because then I can. So I got 1280. Put that into the memory. 2 times 0 plus 1. That's 1. Right?
Yeah.
Mhm.
Okay. So 1 divided by 1280. Oh, hang on. 1 divided by 1280. I got 0.00078.125.
Yeah.
Are you guys? Okay, so that's t. So I'm going to just remember that before I forget it. Okay, so how do I convert that to distance?
So that's in seconds. So
Would you,
we should use these.
would you multiply it by 1,130?
Bigger number.
You multiply it by close. Multiply it by 1.13.
Oh.
Oh,
wait.
because we're a millisecond.
We're in
Or no, we're
seconds.
trying
Oh no,
to
that
do
is seconds. You're right. No, this is seconds. You're right. You're right. So so yeah, the first thing we'd want to do is convert that to milliseconds. Right?
For 7, 8, that number.
Yeah.
T. Okay.
So we convert that to milliseconds. We just multiply by 1,000, right? So times 1,000. That's 0.78125 milliseconds. And then we multiply that by 1.13 feet per millisecond. Because that's that number I told you to memorize. 1.13 feet per millisecond. And you get 0.8828125. So the answer here is 0.88 feet. So a little over half a foot, right? Offset those two speakers. Point them at somebody. 640 hertz will cancel out first. Those of you who are in the engineering class, remember I did that. Remember I offset two speakers and I pointed them at you last semester?
Oh, yeah.
And this is what you heard. Okay? Okay, this is the classic. This is the one that, our Achilles heel, the thing that gets us every single time. So, It's that middle of Act 2 love ballad when the two love interests finally profess their feelings for one another, and they come within 6 inches of each other's face and hit a beautiful harmonized held note. And their mics are 6 inches apart. What happens if you put those two faders up and mix it into the system? All right. So I'm just going to let you guys do this. So I'll write it out. You tell me what the answers are. Okay. So let's start with the cancellations. How many? Let's do 3. 3 each. Just, we don't want to be here forever. So let's start with cancellations. So 0 for the cancellation is going to equal 2 times 0 plus 1 divided by 2 times t. Now what is t? Well, let's see if we can figure that out. 6 inches is 0.5 feet. Yeah? So what would that be in milliseconds?
0.565 milliseconds.
Well, the time should be a lower number than the distance, remember?
Maybe 0.44.
So you want to divide this by 1.13.
Yeah, that's what I did.
So 0.5 divided by 1.13?
0.44247.
That sounds more reasonable. Did you take 0.5 divided by 1.13?
I did point 1.13 divided by 2.
That's not the right thing.
Okay.
So 0.5 divided by 1.13 gets you what? 0.44 what?
0.4424778761.
So 0.25. Okay, great. And then that's milliseconds, right? So in seconds, that would be what?
You just times this by 1,000, right? So
442.477.
yeah, sounds right. That's what I got.
Say that again?
442.4.
No, it's the other way. You got to divide. Should be a smaller number, right?
But we're going.
We're in milliseconds. We want to go to seconds.
Oh, okay.
Yeah.
0.000425.
0.00
425.
3 zeros.
Yep.
4.
25.
Well, that's
Technically,
the
we
second
don't need
bit.
the what?
There's 2 4s.
Should be 2 4s, right?
Oh yeah, sorry. Yeah, 425.
Hang on. 4 4 2 5. Yeah.
So really, I guess instead of pulling out your calculator, you could just move the decimal.
Yeah.
You could.
over.
You could. You just move it 3 places and you get the answer. Yep.
Usually I do 3 zeros.
That would work. Okay. There's t. So we got t. So 2 times t. Okay, what is this? This will be 2 times 0. So it'll be 1 divided by 2 times t. What's 2 times t?
0.000885.
Okay. That dot's in a weird place, but you know what I meant. Okay, so 2 times 0.000885 is what?
1,000.
Or no, sorry. We already multiplied it. So 1 divided by 0.000885.
1,129.9435.
I got the same.
1129.54?
9435.
94. Okay. So 1,129.94 hertz. That's the first cancellation. Okay. So let's go to the next one. 2 times 1 plus 1 divided by 2 times t. What's that?
I got 3,389.831 hertz.
I got this.
Anybody else get that? That's 2. I need one more with that same answer. All right, Emma got that. It must be right. Okay. So now we'll go to 2c. So this would be 2 times 2 plus 1 divided by 2t.
I got 5,649.71.
Has anyone picked up on the pattern here yet?
I'm close to it. I gotta keep it under 5,650.
That's fine. Anybody picked up on the pattern? Once you get the first cancellation, second cancellation is times 3.
Yeah.
Next cancellation is the first times 5. And you just do all times it by odd number multiples every time.
So do you times it by a prime
What?
prime number? Or, no, that's not.
So you multiply to get the.
So just do me a favor. Take 1029.94 times 3.
Ah,
Okay, now do 1129.94 times 5.
How do you know these numbers?
Because it's 2 times the integer plus 1.
Yeah, I'm just like this equation. This
Oh.
equation is meant to just like make it really dead simple. You don't have to understand what's happening in order to do this math. I'm just saying, like, if you realize if you do enough of this math using this simple little equation, hopefully you see the patterns. And ultimately, the pattern is this: if you can just figure out that first cancellation, all the other cancellations are just odd number integer multiples of that. Yeah? Okay. Should we do some reinforcements?
Sure.
I'm running out of space here on my screen. So 0 reinforcement is going to be 0 plus 1 divided by t. So 1 divided by 0.000885. No, 1 divided by 0.0004425. Right? What's that?
2,259.887.
59.888?
88.
89?
Yeah.
It's not the same thing.
It is 6, 7, 8, 9. It's a new thing.
Oh.
It's a 41. I'm sorry, guys. Too on mine.
Okay. 1r is going to be 1 plus 1 divided by t. What's that? So 2 divided by 0.000445.
I got 4,519.774.
Yeah. Same.
Same.
I got a different decimal.
That's all right.
You should be able to do that.
Probably not.
That's all right.
Probably not.
Okay, so now we're going to do 2 plus 1 divided by t. So 3 divided by 0.000445.
$6,779.66.
6,779.
0.66.
6 hertz. Okay, so have you seen this pattern now? Take the first cancellation, 1,029.94 times 2.
Yeah, that's what I
1,000.
The number into
Yeah. 1,029.94 times 4 gets you that. Times 6 gets you that. See how that works? It's ultimately really simple. All right, how we doing?
Where did you said 2 times 6, 6 times what number is gonna, go the last number, why is it not 4?
Well, we already did 4. So I was just saying, like, if you take the first cancellation, times that by 2, you get the first reinforcement. Take that number, now times it by 4, you get the second reinforcement. Take that number, times it by 6, now you get the third reinforcement.
Oh, you're by the cancellation times 2.
Yeah.
Times,
Is
okay.
it a cancellation or
Yeah.
is it a reinforcement?
The first
First cancellation is that's where you start from.
So that's always like,
Mhm.
that's your
Oh,
favorite
okay,
number.
understood.
Yeah.
Okay.
Yep. First cancellation times 2 will get you the first reinforcement. First cancellation times 3 gets you the second cancellation. First cancellation times 4 gets you the second reinforcement.
So,
Okay.
so far.
Yeah.
Okay.
Oh, that's why. The Wi-Fi just kicked me off, which just lost my iPad. Come on.
Do you need Wi-Fi?
Well, yeah, for this to work.
For the pen?
Yeah.
Wanna borrow my hotspot?
No.
Stuff.
Okay. Let's see if he'll give it to me now. Give it to me. There we go. Okay. We got time for more. How many more do I have? Oh, yeah, just one more. Let's just do this one more. Come back. Come back to me. Okay. So, comb filter has its first cancellation at 300 hertz. What frequency would the second cancellation be? Well, using our little shorthand, we could do this really quick, right?
300 times 3.
900?
Yeah. So it should be 900 hertz, right?
Yep.
If our pattern holds up. Let's just test it and make sure. Okay? So,
Yeah.
let's just prove the theory here. So let's first find t. So t is going to equal 2 times I plus 1 divided by 2 times frequency. Okay, so 2 times I is going to be 0 plus 1 divided by 2 times 300, which is 600. So this is basically going to be 1 divided by 600. And what's that?
900, that's my guess.
20.
Should be.
6.
There you go.
Wait.
7.
Yeah.
Point 0.0067.
167. Wait, why don't you have a lunch early?
I have a 1.
Just. Oh.
1 divided by 600.
Yeah, mine is 0.0166666.
6, 7. Yeah?
Yeah, 1 6.
Okay, so that's t. Okay, so second cancellation is going to be 2 times 1 plus 1 divided by 2 times 0.00167. Yeah? So what's that? Well, 2 times 1 is 2, plus 1 is 3, so 3 divided by 2 times 0.00167, what's that? What do you get? Should be 900 hertz-ish.
Yeah.
Yeah?
900 hertz plus a couple decimal points. Like 0.09000.
Yeah.
I did put it on the 30s.
Anybody else get that? Anybody else? I need 2 more people before I'm going to count this right. Okay, Ben got it.
Um,
Sam got it? Okay, there we go. See? It works. Okay? Questions? Okay, I have 2 more things I want to throw at you that don't require math. Well, they do, but we're not going to do it.
Okay.
First is principle of diffraction. The idea here being what happens when sound runs into something. Well, we're going to study that in a bit more in depth later in the semester in our section on acoustics, but this is a little teaser. So if this sound wave that's propagating through the air encounters an obstacle that is in its way, it's in the path, what could happen? Well, there's a lot of things that could happen, turns out. The thing that we're focusing on is how does it get around it? Well, it'll get around it eventually, unless it's an infinite baffle, which is more common than you might think. But for purposes of today's discussion, we're assuming not infinite baffle. Like this thing is not infinitely large. It has some finite size. Well, if that finite size is significantly larger than the wavelength of that sound, then it's going to have a hard time getting around it, right? That obstacle is going to, measurably impede the progress of that frequency. And so what happens is, this is the part of the top. It'll get around it, but there's going to be this area where there's a little bit of a hole. Like if you stood right on the other side of that wall, you would not hear a whole lot of that frequency. Okay, because it's having a hard time getting around that. It gets around it eventually, but you have this sort of shading that happens. This is why if you ever drive down the interstate, you notice they have these big walls, big concrete walls that they on top of a little mound of dirt usually. That's why they're trying to build a barrier that's tall enough to create an acoustic mask or acoustic shadow for the house that's right on the other side of that wall. So the house that's right on the other side wall is in that acoustic shadow. Now, the house across the street from that house is going to hear it, okay? But the theory is by that point, the decay over distance has taken over, and it's gotten quieter just because it's traveled farther, okay? But that's what they're doing, is they're trying to create that diffraction shadow for that house that's right next to the interstate. More interestingly, I think at least, is if the obstacle is smaller than the wavelength of that frequency, then it's effectively invisible to that sound. Like the sound wave will go around that obstacle as though it wasn't even there. It's called acoustically transparent. So that obstacle that is smaller than the wavelength, it's not going to impede the flow of sound in any significant way. Why is this important? Well, can you see this grate? Everybody see that right here?
Mm-hmm.
Describe it for me. Pretend I can't see it. How would you describe it?
It's gray, metal, with slots.
It's with slots. Interesting. So that's normal, actually. Human beings would describe this going, yeah, it's got a bunch of like holes, these slots in it. Okay? That's not how the sound wave sees it, though. But the sound wave sees is like it's gray and metal. Well, the sound wave doesn't know it's gray, but it does know it's metal. And it's got a bunch of little bars. The sound sees the obstacle. It doesn't see the gap between. We see the gaps, the sound sees the obstacle. And in this case, that obstacle is this big, which is, smaller than the wavelength of almost the entire audible spectrum, which means sound is going to go through that grate completely unimpeded. So sound sees the obstacle. Where would that concept come into play in real life, do you think? Ace?
Hiding a speaker somewhere.
Oh yeah, we always want to do that, right? Nobody likes to see speakers. They always want to hide them.
It's like the rock speakers that they have in like theme parks or something.
Yeah, and so everyone wants, you want to cover it with something. Well, and again, like if you're thinking about it like a human would think about it, you're like, well, I'm going to make a bunch of holes in the thing that I'm covering it with so the sound can get out. And that's not the way you should think about it. It's not about putting sufficient number of holes in it. It's about creating obstacles that are the right size. And you can create that by drilling holes. But it's more about the gap, it's the space between the holes is more important than the actual number or size of the holes themselves. What makes it acoustically transparent is the size of the gap between the holes. As long as that gap is smaller than the wavelength of the highest frequency you want to get through that, then it'll be fine.
So what would that like?
Well, I don't know. There's a lot of ways you could do that. Like, so you could have teeny tiny holes. Like, look at I don't know if you can, those of you that have computers, you might see there's these little, on the top of mine, if you look really carefully, there's little tiny holes, right? And that's where the speakers are. The holes, you almost can't see them. They're so small. But still, sound comes out really well. Why? Because the gap between those holes is smaller than the highest audible frequency.
So is that the same for an instrument then?
Yeah, any object, right? So now think about a scenario where we want to stop the sound. Maybe it's the opposite thing. Maybe we've got too much sound over here and we want to stop it, like offstage noise, or you've got a bunch of musicians sitting, on a stage or in a pit or something like that, and you're getting bleed from between the microphones, or this musician is saying, hey, this person's too loud or blowing me away, and you want to stop that. Well, what's it going to take? A pretty big wall, right? If it's a tuba, it's going to need a pretty big wall that you're going to have to put between there in order to stop those low frequencies.
Does thickness also matter in this regard?
Not really. I mean, it does. It only in the sense that if it's too thin, it could potentially vibrate sympathetically. Like it could be excited. It could be moved by that sound wave and retransmit it. So it matters in that sense. But an inch thick versus 4 inches thick would be functionally equivalent. It's really more about the size of that wall that you put in between them. You put a wall this big next to them, nothing. It may as well not be there. It's not big enough. It's not a big enough obstacle. Let's say that tuba is averaging 200 hertz. Well, what's the wavelength of that? What's the wavelength of 200 hertz? Just do it in your head real quick. Speed of sound divided by the frequency. 1,000 divided by 200. 5 feet. You got to have a wall that is 5 foot tall and 5 foot wide, at least, in order to have even a hope of creating any kind of shadow. That's big. That's 5 feet by 5 feet. Ideally, it'd be even bigger than that, right? But you'd start at 5 feet. It's big. Okay?
Is this kind of like where drum shields come from? Like,
Yeah.
so that they're not as loud as like, or not as loud, but like to help control some of the sound for the rest of the band.
Yeah. Yeah, the drum shield does nothing to help the audience
Yeah.
because the audience is far enough away that the sound has found its way around. You know, that diffraction thing happens right next to it, but once you get 10, 20 feet away from it, it sounds the same. Sound has found a way around. The drum shield really only helps the people standing right next to the drum set.
Which is good, right?
Yeah, that can be good. But a lot of people who don't understand this concept will tell you, oh, the drums are too loud out in the house. Let's put a drum shield on there. And then they're surprised when it doesn't make a difference. Okay. All right. Anyway, any more questions about this concept of diffraction? These are just some rules of thumb to keep in mind. Okay. All right, next thing is, remember that one time a couple days ago, or last week maybe, when I said, we were talking about the speed of sound, and I said the speed of sound is affected by temperature. And that's true. Sound travels faster in warmer air than it does in cooler air. The warmer the air, the faster the sound travels. Well, okay, that's fine. What if you don't have a consistent temperature? Then what happens? Well, what if you have what's called a temperature gradient? So like in scenario A here, we've got cooler air up above and warm air down below. What's going to happen? Well, the part of that sound that's towards the floor or the ground is going to be moving faster than the part of that wave that's up above.
Does that create its own like cone filtering in a way?
No, but it does have the effect of changing the direction that energy is propagating. So because the sound down here is moving faster and the sound up here is moving slower, it's like it kind of directs that energy up. Like that energy collects up above where the cold air is, because it can't move up there as efficiently. The opposite thing happens if you've got warm air on top and cool air on the bottom. Up on top, it's moving really fast, and down below, it's moving slow, and it has the effect of the sound propagating downward. Well, let's think of some scenarios where this would be true and where we would run into this. So, really common scenario, you're outside, doing a show outside, and you're doing your sound check during the day. Okay, because show's usually later. Okay, do your sound check during the day in the middle of the hot sun. Okay, and you get everything set, dialed in, everything sounds great. Sun sets, it's time to do the show. Why do we wait for the sun to set? Because so we can do cool lighting, right? And so the sun sets, and what happens to the air?
Cools down.
It gets cooler, right? Sun goes down, it's not baking that air, so it cools down. But the ground is still hot because it's been cooking under that sun all day. So you've got the ground is hot, and therefore the air right next to the ground is hot, but the air up above is cool. So what happens is the sound drifts up, and that has the effect of the show sounding quieter down where the seats are. It's like suddenly it seems quieter. It's quieter than it was at sound check. And you're going to think it's because, well, there's all these people, they're soaking up the sound. No. It's because the grass soaks up the sound just as efficiently as the people do. It's not that. The dirt soaks it up too. It's the temperature. You're producing the same amount of sound. It's not getting absorbed. It's just being redirected because of that temperature gradient. So most of that energy is going up above and not actually being directed towards the ears anymore.
So even like, because I always thought that like it was the people coming in the room that was taking away
Yeah.
from like the sound, but I noticed like body temperature sometimes, like
Ooh.
that's like, so is that part of
Yes.
the equation
So
too?
this can also happen inside. So usually big theaters and concert halls and stuff are huge rooms where you can put hundreds, if not thousands of people, and therefore they have air conditioning systems capable of cooling hundreds to thousands of people. How many people are there at a rehearsal?
Not that many.
Not hundreds and thousands, right? Maybe a couple dozen, right, are there for the rehearsal. So you've got this air conditioner that's designed to cool 3,000 people, and it's cooling 20 people. And everyone's freezing. You're always freezing in rehearsals, okay? Because the air conditioning, everyone's bringing coats, right? That's why, because the air conditioning's running, and it's trying to cool 3,000 people, and there's 20 people in the room. Okay, so you do your rehearsal, you set all your levels, everything sounds right, everything's great, and then you get to the performance, and suddenly you fill this room with 3,000 98.7 degree hot water bottles, which is basically what human bodies are, right? They're enormous hot water bottles. And you fill the room with 1,000 of them, and you sit them on the floor. Well, what happens to your air? It gets really hot down there at the floor, right? Because you just filled it full of heating pads. And where are the vents that the air conditioners? They're usually up above, right? Right? Because the cold air goes down, right? So fill the room, air conditioning kicks in, and suddenly you've got a temperature gradient, right? It's hot down there in the seats, cool up there in the ceiling, and same thing, sounds drifting up. And so it sounds quieter. Beginning of the show, you're like, it sounds quieter. Why does it sound quieter? Temperature's changed pretty dramatically in this gradient that makes the wave drift up. Yeah.
Can walls help that with reflection of like making it like help the sound?
Sure. I mean, that's hopefully the walls are creating helpful reflections that help the sound propagate, but that doesn't change the fact that the temperature gradient's happening and it's drifting up, right? Those walls are there whether it's no matter what the temperature is. Now, if sound is getting significantly slower, if it gets cold enough, the sound can get slow enough that those walls become not helpful reflections. I've actually had that happen to me once, where it was like sound slowed down significantly, that the reflection times of the walls didn't make any sense, and they were turning into echoes, not early reflections. Crazy. It was in an empty building I was brought in to do an acoustic consulting in, and they gutted it, and it was in the middle of winter, and it was an empty room with no air handling, and nothing. And they wanted while we were making measurements and everything, and nothing made sense. Like none of the measurements made any sense. Like it's like we're measuring a room that's twice as big as this, and it took us forever to realize it's just that freaking cold, that the sound has slowed down that much, that our measurements still make sense. Okay, so it was the day was kind of a bust, but the good news is in that temperature gradient scenario, eventually that will even out, right? If you don't overreact and you just wait a little bit, eventually that air conditioning will start cooling down all those hot water bottles that are down on the floor, and that the temperature gradient will flatten out a little bit, and the sound will start doing something more like what it was doing in rehearsal. So don't overreact and change everything in the first 10-15 minutes of the show, because it's gonna fix itself mostly, pretty soon. Yeah.
I wish I knew this like over Christmas break, because I learned this gig, and like I was at A2, and me and the guy, like, he was the mixer, and we'd had our rehearsals and stuff. Empty room, large empty room.
Yeah.
Sounded great. People come in, I'm like, oh, all the bodies are soaking up the sound. But no, it was the air.
Yeah.
It makes so much more sense.
Yeah, I mean, generally, like seats, if you're in a venue that has like, concert or theater seats, those seats usually have absorptive qualities to them. If you look on the bottom of the seat folds up on the bottom of the seat, there's holes on that, and that's so that the cushion of the seat absorbs the sound, right? So they're trying to make the empty seat absorb the sound at a similar rate as the person sitting in the seat would. It's not exactly the same, but it's close. And so that difference between body in the seat versus body not in the seat is not as big of a difference as you might think. It's a little bit. I mean, yeah, sure. I mean, bodies do absorb sound a little bit, but that does not fully explain what you're hearing, right?
Because then after a while, like literally, like you said, 10 to 15 minutes after the
It
show
gets better.
started, it sounded great.
Yeah, that's why. Air conditioning kicked in, everything was fine. Okay? All right. The opposite thing can happen if you've got warm air on top and cooler on the bottom. It's suddenly things will start sounding louder, but also it'll be inconsistent, right? Because it's like leapfrogging itself. It's like the sound is like tumbling across the ground, and so there will be parts where it sounds really loud, and then you go several feet further away, and it gets quiet again. Then it gets louder, and then it gets quiet. So you end up with this like weird ripple that again evens out eventually, hopefully. Not much you can really do about that. Wind has an effect on this too. So here we've got wind. If the wind is blowing this way, and here's our sound source. So sound source blowing, trying to propagate sound against the wind. Well, listen, folks, sound is air. Okay? Sound is air. Sound is air moving, actually, which is not unlike wind. Okay? So going against the wind is going to affect the way the sound propagates, right? That wind is pushing against that whatever is generating that sound, and it's going to impede how effectively that sound propagates. And it has the effect of the sound energy drifting upwards against that barrier, that wind resistance. And again, it'll sound suddenly quieter to this person here than it did before when the wind wasn't blowing.
No, we blew the sound away.
Yeah, exactly. The opposite happens over here. So here's your person standing here, and if the wind is going this way, it's like helping the sound, right? It's pushing it a little harder than it's going by itself, and it ends up like drifting down to the ground because it's pushing it down to the ground. And so suddenly it's louder here. What do you do about that? Well, if you've ever done, again, shows outside is where this happens the most. Have you ever done a show out? Anybody done a show at the beach? At the beach? No? There's usually wind coming off the ocean, right? And everybody wants to do the show at the beach, right? Because you want the waves in the background and the sunset and all that kind of stuff. Well, there's this wind coming, right, from behind you. And so you end up, like, to compensate, you end up aiming your loudspeakers high so that the wind will catch the sound and then boom, hit it down to the seats in the right spot. If you aim it normally like you would if there was no wind.
That's why they do that?
Yeah.
How do you know, like, how far up to angle?
You guess.
All this math and you just guess.
Yeah.
What about the temperature as well? Like,
Yeah, it makes a difference for sure. There are actually some some digital system processors that have temperature sensors in them. So you can hook up a temperature sensor to your processor, put that out into the venue. It'll measure the current temperature, and it will adjust the delay values according to the speed of sound for that temperature to keep everything lined up. Yeah. I've never actually done that, but they exist. Okay? All right. So we're out of time. You now know everything you need to know to do all the math that's in the assignment on Canvas. I will warn you, the last question is about a specific venue here on campus. The idea is I would like you to actually go to that place and look at it and try to figure out how to answer the question, because I'm trying to get you to visualize this concept in some real life thing, okay? You could just get up the CAD file and figure it out that way if you want, but I'd encourage you to, even if you're going to do that, go to the place and pull up the CAD file as you're looking at the real thing, okay? It's a matter of visualization. All right? Yes, Charlie?
With the quiz, is it timed?
No.
Okay, so we can start